All right, so let's go ahead and get started. What we want to do today is go through some of these problems on the practice exam. And they take up a bunch of space, so we're not going to write on this sheet. We're going to amend it. And add to the bottom. One quick second. We have two versions going here. Let me make sure I have the right. Oh yeah, I think that's the right one. Okay. So let's go ahead and start with problem 1. And just work through each one of these. Delay. All right. So okay, I think our colors work. All right, let's start with problem 1 here. Find the limit as x approaches 4 of x squared minus 2x minus 8 over 7x minus x squared minus 12. The first thing that we want to do with any limit problem is to try direct substitution. And the idea is that if we try it and it works, then we're done. And if we try it and it doesn't work, it usually gives us some information. So I'm just gonna do direct substitution and plug in, right? 4 squared minus 2 times 4 minus 8 in the numerator, and 7 times 4 minus 4 squared minus 12 in the denominator. And I'm gonna use my calculator because I think I might have used up all of my good arithmetic skills already today. Okay, but just to double check and make sure we didn't make a mistake, we have 0 over 0. So this tells us two things. One, we weren't allowed to do direct substitution, but also because plugging 4 in to the numerator gives me 0, and it's a polynomial, that means that 4 is a root, so x minus 4 is a factor. And same thing with the denominator, because it's a polynomial, I know that x minus 4 is a factor. So we can't do direct substitution, but we can do is factor this, and I know that x minus 4 is going to be a factor of the top, and I know that x minus 4 is going to be a factor of the bottom. So just got to figure out what we have left. In the top, these are written in nice order, right? So x squared minus 2x minus 8. So when I'm FOILing out, I'm going to have to multiply an x by a second x in order to get x squared. And when I FOIL and do the last terms, negative 4 has to be multiplied by something to give me a negative 8, so that has to be a positive 2. There's no other choice. Okay, so the factoring here is a little bit easier than, in like a normal algebra class where we have no extra information. Okay, for this other one, it might be helpful to rewrite this in order, right, as a negative x squared plus 7x minus 12. You don't have to, but then it's a little bit easier to see, oh, I want a negative x squared, so I'm going to multiply this x by a negative x. And then to get negative 12, I have to multiply a negative 4 by a positive 3. So we can write this as negative x plus 3, or it's commonly written just as like a 3 minus x. Either way works. We should double check these, right? So on the top one, if I were to FOIL it out, I get x squared plus 2x minus 4x minus 8. And I can see, oh yeah, that matches. 2x minus 4x will give me the minus 2x. On the bottom, x times negative x is negative x squared plus 3x. Negative 4 times negative x is a positive 4x. And then negative 4 times positive 3 is the minus 12. And we say, oh yeah, 4x and 3x will give me the 7x. And it all works out nicely. So we say, great, I can cancel my x minus 4s because in a limit, x is not equal to 4. So this is equal to the limit as x approaches 4 of x plus 2 over negative x plus 3. And now we can use direct substitution. So when I use direct substitution and plug in, I'm going to have 4 plus 2 over the opposite of 4 plus 3. So we get 6 over negative 1, or just negative 6. All right. So let's just keep plotting along. Number 2, the limit as x approaches 3 of x squared plus 2x minus 15 over x squared plus 2x plus 10. Okay. Once again, I'm going to try direct substitution. Okay. So we get 3 squared plus 2 times 3 minus 15 over 3 squared plus 2 times 3 plus 10. And in the numerator, I'm going to have 9 plus 6 minus 15, which is 0. In the denominator, I have 9 plus 6 plus 10, which is 25. And 0 over 25 is just the number 0. I don't have a 0 in the denominator, so direct substitution is okay here. And then we're done. Okay, so if you weren't sold on starting your problems with direct substitution before, hopefully you are now. All right, let's look at problem, let's look at problem 3. We have the limit as x approaches negative 5 of 2x squared plus 11x plus 5 over 3x squared plus 25x plus 50. Okay, and this looks like the ones that we were doing earlier, but a little bit messier. So let's just go ahead and follow the same procedure. Try direct substitution. Okay, so we have 2 times negative 5 squared plus 11 times negative 5 plus 5 in the numerator. And we have 3 times negative 5 squared plus 25 times negative 5 plus 50. Okay, these are big messy numbers, so I'm going to make sure to use my calculator. One of the things that you want to be careful with on your calculator when you're plugging something like this in, see if I can show you. Just want to be careful with negatives. Okay. So just real quick to show you what I mean. If I write 2 times negative 5 squared, that's going to give me negative 50. If I write 2 times, and I put my negative 5 in parentheses and square it, I get positive 50, which is what I want, because I want the negative, the whole x value gets squared. Okay, so when you're plugging into a polynomial like this, make sure you put your negative 5s in parentheses, especially where it's squared. Otherwise, you'll get a wrong result. Okay, 0 over 0, once again, that tells me I'm not allowed to use direct substitution, but it also tells me that this will factor. So negative 5 is a factor, so x minus negative 5, or x plus 5, I'm sorry, negative 5 is a root, so x plus 5 is a factor. In the numerator, to get a 2x squared, I have to multiply x by a 2x. To get a 5, I have to multiply a 5 by a 1. And so I double check, right? 2x squared plus x plus 10x will give me my 11x, and then 5. In the denominator, to get a 3x squared, I have to multiply x by 3x. To get a 50, I have to multiply a 5 by 10. And once again, we double check, right? So plus 10x plus 15x will give me a positive 25x in the middle, so everything works out. The limit ignores what happens exactly at x plus 5, so I can cancel here. So this is the same as the limit as x approaches negative 5 of 2x plus 1 over 3x plus 10. And now we use direct substitution. And I get 2 times negative 5 plus 1 over 3 times negative 5 plus 10. So I have negative 10 plus 1 is negative 9 in the numerator. Negative 15 plus 10 is negative 5, and a negative over a negative is positive. Okay. And for a problem like this, and for longer problems, it looks a little bit neater to summarize our result at the end, right? So we can write, so the limit as x approaches negative 5 of 2x squared plus 11x plus 5 over 3x squared plus 25x plus 50 is equal to 9/5. And that's my answer, but remember we want a solution, so we have to write all of the steps as we go. A couple of things that I want you to note that are important and easy to forget or misplace as we go. This first limit is equal to the second limit, and the second limit is equal to the third limit. And this third limit's the one I can do direct substitution on, right? So writing limit here is important. Once I do direct substitution, I don't need to write limit in front anymore. Okay. So it's good to keep good habits with notation as we go through. All right, let's look at problem 4. The limit as x approaches negative 7 of x squared plus 3x minus 28 over 2x squared minus x minus 105. Okay, let's try direct substitution. So we have negative 7 squared plus 3 times negative 7 minus 28. In the numerator, and 2 times negative 7 squared minus negative 7 minus 105 in the denominator. Okay, so when I plug in, I get 0 over 0. Okay, so same or similar story to problems 1 and 3 here. So I'm going to factor and cancel. And I know that x plus 7 is one of my factors. Okay, to get an x squared, I multiply x by an x. To get negative 28, I have to multiply a 7 by a negative 4. Okay. To get 2x squared, I have to multiply x by a 2x. And to get negative 105, I have to multiply a positive 7 by a negative, I believe that's 15. And then we double check, right? So x times x is x squared, minus 4x plus 7x will give me a positive 3x, and then 7 times negative 4 is negative 28, so that works. X times 2x gives me 2x squared, minus 15x plus 14x will give me a minus x, and then 7 times negative 15 gives me a negative 105. Okay, so that does indeed factor correctly, like this. We cancel away our x plus 7s, again, because in a limit we ignore what happens exactly at negative 7. So we are indeed able to cancel those away. And we get the limit as x approaches negative 7 of x minus 4 over 2x minus 15. And now we use direct substitution. And we get negative 7 minus 4 over 2 times negative 7 minus 15. So negative 11 over negative 29, or 11/29. Now, I do have a chain of equality from the start of my problem to the end. So in the last problem where I rewrote it, I don't have to do that in order to logically see that the problem I started with is equal to 11 over 29, because I have an unbroken chain of equality. Okay? So it's really just cosmetic. But if you have a problem where you have if you have a problem where you have to do some scratch work or leave your chain of equality to go solve something else, then you want to make sure that the logic flows neatly. Okay. Let's say, all right, so the limit as x approaches negative 7 of x squared plus 3x minus 28 over 2x squared. Oops. Over 2x squared minus x minus 105 is equal to 11/29. Okay. Second, it's over. Somebody's trying to get in. All right, let's look at the next problem. And for this one, I'm ready for something other than factor and cancel. So let's hope that we get something different here. So the limit as x approaches negative 1 of 5 minus x over x plus 1 squared. Okay, so let's try direct substitution. When I try direct substitution, I have 5 minus negative 1 over negative 1 plus 1 squared. So in the numerator, I get 6, and in the denominator, I get 0. So now we have something different. I don't have a 0 over 0. I do have a 0 in the denominator, so I'm not allowed to do direct substitution. But a non-zero number over 0 tells us that we have an infinite limit. So the way that we handle this problem is going to be a little bit different. Because it's an infinite limit, we know that it's either going to go to infinity or negative infinity, or it's going to split and do something different from both sides, and so the limit won't exist. Right? So if I look at each one side individually, there's only two options, infinity or negative infinity. So I'm going to look at my original limit from the left and also from the right. So then for the one-sided limits, I know that each one-sided limit is either going to be infinity or negative infinity. So I don't have to keep track of numbers, I just have to keep track of whether it's positive or negative. Okay, so if I look at this first one, when I plug in something close to -1, I'm going to get approximately 6. So this is going to be a positive here. And in the denominator, if I plug in something very close to -1, but from the left, then I'm going to get, when I add 1, it's going to be close to 0, but it's going to be negative. However, when it's squared, I get a positive over a positive, which is positive infinity. Okay. For the other limit, once again, when I plug in something very close to -1, I'm going to have approximately 6, which is positive. And here, when I plug in something close to -1, I'm going to be about 0 when I add 1. But if I'm approaching from the right, it'll be bigger than -1. So when I add 1, it'll be a positive. And when I square it, it becomes positive anyway. Okay, since these two match, the limit as x approaches -1 of 5 minus x over x plus 1 squared is equal to positive infinity. And you don't have to write positive. If you just write infinity, that's fine too. Okay. All right. It's very important that you have a reason why. If I just look at this problem and I say, okay, that's infinity, that's not really showing an answer. Okay, so although the answer is that the limit is positive infinity, you want to make sure that you're showing some line of thought here. And I didn't do a whole lot of writing to do that, but I did break it up. And so, here's the question: is there a mathematical way to express the way that we solve infinite limits? Because my notation here is kind of sloppy, right? Where I just write the positive over a negative bit. Okay, and I think that what we're trying to do, once we've already established that it's going to positive or negative infinity, all I'm doing is keeping track of the signs. So it's kind of like when we were looking at things numerically, except I don't have all of the infinite many different numbers as a possibility. I just have positive infinity and negative infinity. So I'm just trying to figure out which one it is. If I wanted to write this more formally, this isn't how we would do it, but I don't want to make things more confusing than they need to be. So is there a more formal way that we could express these? Yes, but I don't really recommend it for right now for what we're doing.
Okay, thank you. Sorry, I asked a too complicated question there.
No, that's fine. Another way that you could go about that. Well, we'll just leave it at this for now. I don't want to get confusing and talk about too many different
Yeah,
ways to do
that's
the
fine.
same thing.
I just wondered if there was an easy answer, but it sounds like there's not. So
Yeah.
I'll look at that on my own time or something.
Okay. All right, let's look at problem 6. Here we have the limit as x approaches 6 of 3x squared minus 17x minus 6 in the numerator, and x minus 6 squared in the denominator. What's nice here is that the denominator is already factored for you, so you don't need to FOIL that out. That's not helpful. In other problems, we wanted them factored. So we're going to leave the denominator as it is. I'm still going to start the same way that we try other problems with direct substitution, because that kind of gives me a sense for what's going on, right? So we put in 3 times 6 squared minus 17 times 6 minus 6 up top, 6 minus 6 squared in the bottom, and I'm going to use my calculator just to double check in the numerator here. I trust myself to compute the denominator because 6 minus 6 is 0. Okay, so I am going to have to factor this. But as I said, the denominator is already factored. So no worries there. If you want to write it as 6 times x minus 6 times x minus 6, that's fine. In the numerator, I know I'm going to have at least one x minus 6 factor. So we figure out what the other factor is. Okay. in order to get a 3x squared, I have to multiply x by 3x. In order to get a negative 6, I have to multiply negative 6 by a positive 1. Okay, and when I double check it, I get 3x squared plus x minus 18x will give me minus 17x, and then the minus 6. So we say, all right, fantastic. Cancel away the x minus 6 terms. So now I have this new limit, 3x plus 1 over x minus 6. And we say, all right, let's do direct substitution. And here, when I try direct substitution, 18 plus 1 is 19, I get a non-zero number over 0. And so that tells me, oh, wait, I have an infinite limit. So we didn't start with a non-zero number over 0. But when you get 0 over 0, anything is really a possibility. And this is a good example of that. So what we're going to do now is treat this as an infinite limit. And we're going to look at the limit as x approaches 6 from the left, and the limit as x approaches 6 from the right. Okay. And once again, I just want to keep track of the signs, right? When I put in something close to 6, I know in the numerator I'm going to get about 19, right? So that's positive. And when I put in something close to 6, I know the denominator is close to 0. But if I'm approaching from the left, when I subtract 6, I know that my numbers are starting off more negative than, or sorry, smaller than 6. So when I subtract, I'll have a little bit of negative, so it'll be a negative. And when we approach from the right, the numerator is still approximately 19. And in the denominator, I'm putting in x values a little bit bigger than 6. So when I subtract 6, I still have some positive left over. Okay, these don't match. So the limit as x approaches 6 of 3x plus 1 over x minus 6 does not exist. Therefore, the limit as x approaches 6 of 3x squared minus 17x minus 6 over x minus 6 squared does not exist either. Okay. So here we definitely had to, combine some ideas together. All right, let's go ahead and look at problem 7. Problem 7 is asking us to come up with a graph, and we're given a bunch of information, so let me write that information down. We need the limit as x approaches negative 4 from the left of f of x to equal negative 5. The limit as x approaches negative 4 from the right of f of x to equal negative 1. F of negative 4 needs to equal 2. Then we need f of 0 to equal 3. The limit as x approaches 3 of f of x should be 7. F of 3 should be 0. And finally, the limit as x approaches 5 of f of x should be equal to infinity. Okay, so let's go ahead and make some axes here. Oh. There we go. And I'm just going to make some marks on my axes, right? We need to go as far left as negative 4. This far right is 5. Okay, and we'll make some marks on the y-axis. Okay, so the way that I like to put this together is just to do a little piece of the graph to match the piece of information, and then I can stitch it all together. So as we approach -4 from the left, so to the left of -4, we have to approach -5. So I'm going to put an open dot there and then just approach that. Okay. As I approach -4 from the right, I have to approach -1. Okay, so I put an open dot there and approach, and go up or down, it doesn't really matter. If we need to change it later, we will. When I plug in -4 exactly, we get a y value of 2. Put a closed dot there. Okay. F of 0 is 3, so when I plug in an x value of 0, we get a y value of 3. The limit as x approaches 3, it doesn't say left or right, that means both sides. It has to be 7. So this has to approach 7 from both sides. F of 3 is 0, so when I plug in 3 exactly, I get 0, so that's a closed dot here on 0. And finally, the limit as x approaches 5 has to be infinity, so I'm going to put a vertical asymptote here. And then just approach infinity. For this side, I'll just pick that up and continue it. And we can make these connect now. Right? Make your graph look nicer. One of the key things when you're creating a graph of a function is to make sure that it passes the vertical line test. So you definitely don't want a graph that has pieces that do this, right? Where, a vertical line would hit it twice. So, that's something to be aware of. Okay, but otherwise, piece little parts together at a time, and we put all together at the end. All right. Let's look at problem 8. Determine if this function is continuous. Okay, so let's write down the function. We have f of x equals 5 minus 2x if x is less than 3. -1 if x equals 3. And x minus 1 squared if x is greater than 3. Okay, we want to look at, is this function continuous at x equals 3? So I'm going to write down our definition of continuity. So we kind of have 3 conditions. We need that the limit exists. Second, that the function value exists. And third, that the two match. Okay. And to show that the limit exists, what we're going to do is we're going to look at the limit from the left and the right. We have to do that in this case because if I just write down my function f of x, I don't know what formula to use that's based on the x values. So if I'm looking at approaching 3, my formula is different whether or not I approach from the left or the right. So I can't compute this limit directly, but I can compute the one-sided limits directly. Okay. So the limit as x approaches 3 from the left of f of x is equal to the limit as x approaches 3 from the left. Since I'm approaching from the left, x is less than 3. When x is less than 3, my formula for f of x is 5 minus 2x. Okay, so now I have a formula that I can use. And since this is a polynomial, I can just plug in and use direct substitution. Okay, so I get 5 minus 2 times 3, which is -1. Okay. Now I'm going to look at the limit as x approaches 3 from the right. As I approach from the right, my x values are bigger than 3. When x is bigger than 3, I use the formula x minus 1 squared. So I can replace my f of x with x minus 1 squared. And now I use direct substitution. So I get 2 squared, which is 4. Okay. Now, at this point, the limit from the left and right do not match. So that means that the limit as x approaches 3 of f of x does not exist. And that's one of the conditions I need. I need that limit to exist and, equal the function value. If the limit doesn't exist, then it's not continuous there. Okay, so f is not continuous at x equals 3. So when I'm determining whether or not a function is continuous, it needs to have all of the conditions. So if it's missing one of them, then it can't have all of them. So I'm done, right? So once one of them fails, you can just stop and say, okay, it's not continuous at this point. To show it is continuous, we need to check, all the conditions, right? We would go on and look at f of 3. It exists. We can show that by saying that it's equal to -1, right? So one of the easiest ways to show something exists is to, say what it is. And then we would compare that to the limit. All right, let's look at another continuity question. This is also using a piecewise defined function, but it's coming from a different direction. So here, I'm not really sure what my function is to begin with. We have a formula, but the formula doesn't, it's not complete. We're missing a value. Like there's an unknown a here and an unknown b here. And so we don't really know the formula for f of x. Or another way to look at it is I might have different functions based on my choice of a and b. Okay, so the instructions are to find the values of a and b that will make this function continuous. And when we just say continuous, we mean everywhere, right, or everywhere in its domain. And the only places that it's really going to have a problem is where we change formulas, right? So ax plus b, that's a line. It doesn't matter what my choices for a and b are. It's going to be continuous. But if here, bx plus 2, I have a line, if those lines don't meet up, then the function has a break in it and it's not continuous. So it's where my x values change that, that I want to focus my attention. Okay, so let's look at that. Let's look at we'll start with x equals -1. At x equals -1, if this had any chance of being continuous, then the limit has to exist. So the limit from the left and the limit from the right must be equal, right? So we need the limit as x approaches -1 from the left of f of x to equal the limit as x approaches -1 from the right of f of x. Okay, so let's look at what those limits are, right? The limit as x approaches -1 from the left of f of x, as we did in the last problem, when I look at the one-sided limit, I can now pick one of the formulas, because when I approach -1 from the left, my x values are less than -1. So we have this formula, square root of ax squared. And I evaluate the limit with direct substitution. X is the one approaching -1. So it's the x that I'm replacing with a -1. Okay, -1 squared is 1, a times 1 is 1, so I just have the square root of a here. Okay, the limit as x approaches -1 from the right of f of x, my x values are going to be bigger than -1, so I have this ax plus b. Now don't get distracted. Here, when x is bigger than 3, it's certainly bigger than -1. But with a limit, we're talking about what happens as I approach this value, -1, but I'm really, really close to that value. 3 isn't close to -1, right? We want to think about being infinitely close to -1. So we're going to use ax plus b here. And once again, when I do direct substitution, I have a times -1 plus b. Okay. So if I have a continuous function, then the square root of a will have to be equal to -a plus b. All right, we're going to come back to that. Let's go ahead and look at what's going on at 3. I'll do this one black. Okay. At x equals 3, the limit as x approaches 3 from the left of f of x is going to have x values less than 3. So that's the formula ax plus b. And I do direct substitution because this is a polynomial. So I get a times 3 plus, oops, I wrote a plus 3 where I meant a plus b. So we have 3a plus b. Okay. The limit as x approaches 3 from the right of f of x, we have x values bigger than 3, so I'm going to use the formula bx plus 2. Okay, so we get b times 3 plus 2, or 3b plus 2. All right, so again, that gives me some information for f to be continuous. We need the limit as x approaches 3 from the left of f of x to be equal to the limit as x approaches 3 from the right of f of x. So 3a plus b has to be equal to 3b plus 2. Right. So now, highlight these. Now I have these two equations, and I have two unknowns, a and b, and what I'm doing is solving a system. Okay. So there's more than one way to solve a system. However, there are square roots in here. This is a nonlinear system. So, like, we have to be a little bit careful. But what I'm going to do is, pick a variable, solve for it, and plug into the other equation. The variable that I want to solve for, that I want to get rid of, I want to keep things simple. And a has square roots in it. So I don't want any craziness underneath square roots. So I don't really want to plug into a. So we're going to solve for b. We'll pick the other equation and solve for b. Oops. So when I solve for b, I can subtract b from both sides. Subtract 2 from both sides. So we have 3a minus 2 equals 2b, and then divide both sides by 2. So 3 halves a minus 1 equals b. Okay, that's fine. Now we have a value for b. I can plug that in to my other equation. So I start with the square root of a equals the opposite of a plus b, and we plug in for b to get 3 halves a minus 1. Okay, we'll group like terms a little bit. 3 halves a minus 1a will give me 1 half a. And to get rid of the square root, what I want to do is square both sides. Okay, the right-hand side squared another way to look at that is 1/2 a minus 1 times 1/2 a minus 1, so that I don't lose anything. Right, on the left, square root of a squared will just give me a. On the right, when I FOIL it out, 1/2 a times 1/2 a is 1/4 a squared, okay, minus 1/2 a minus another half a, and then negative 1 times negative 1 is positive 1. Okay, so now I'm going to group some like terms. Negative 1/2 a minus 1/2 a is negative a. And since this is quadratic, what I want to do is get all of the a's on one side. So I'm going to subtract a from both sides. So 0 equals 1/4 a minus 2a plus 1. When I'm solving a When I'm solving a quadratic, I don't really like to have fractions in here. So this is not necessary, but I think it's helpful. Multiply everything by 4 to get rid of the fractions. Okay, so when I take 0 times 4, it's still 0. 4 times 4 is 1, so we just have an a squared minus 8a plus 4. Okay, and then if this thing factors, I would factor it. If it doesn't factor, or if I can't see how to factor it fairly quickly, then we go to the quadratic formula. Okay, as a reminder, the quadratic formula says that if you have ax squared plus bx plus c equals 0, then x is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. In this case, we don't have the same letters matching up. We're solving for a, so a is in the place of x, and this a is a 1, and this b is a -8, and this c is a 4. So we have to be a little bit careful with where stuff goes. Okay, but hopefully this isn't your first time switching variables around in a quadratic formula. Okay, so we have the opposite of the second coefficient plus or minus the square root of that coefficient squared minus 4 times the first coefficient times the last coefficient all over 2 times the first coefficient. Okay, let's see what's going on. -8 when I square it is a positive 64. Okay. And here, 64 minus 16 gives me 48, and it's like, oh, if it was just one off from being a nice number, right? If it was, like a 49 in there, right, a nice even square, then I wouldn't have a square root anymore. Things would come out nice. That's also the situation where it would have factored. Okay, so if it's not possible to factor it, then you're going to have a square root in your final answer here. Okay, so 64 minus 16 is 48. So we get 8 plus the square root of 48 over 2, or 8 minus the square root of 48 all over 2. And this is maybe, a little bit troublesome because now I have two answers. And I say, oh, shoot, well, what do I do? Okay. It's possible that there's more than one A and B that makes this thing continuous. Or it's possible that one of these solutions isn't a real solution. Okay, so what we're going to do is go back and check them. Now, one thing that we can do right away is we can say, well, in the definition of my function, I have this ax squared. If a is negative, then I'm not going to get any real values, right? So that's probably not it. However, both of these numbers are positive, right? 8 is the square root of 64, so square root of 48 is smaller, so when I subtract, I still have a positive number here. Okay. so now we have to compute the b that goes with it. Okay, so we could have a equals 8 plus root 48 all over 2, and then my b would be 3/2 that minus 1. Say, well, seems like a little bit of a mess. We can simplify it. When I distribute the 3/2, I'll just multiply the 3 into the numerator and the 2 into the denominator. And I can rewrite 1 as being a 4/4. So I get 20 and when I combine the fractions. Okay. So I have one possible combination of a and b here. Okay. And then if a is equal to 8 minus the square root of 48 over 2, well, the only difference is that I've changed this plus to a minus. I didn't really do anything with it, right? So I'm just going to skip a little bit of work here and write my value for b. The difficult thing is going to be determining whether or not these both actually work. And what I want to do is I want to check them back into my original function and see what's going on. Does that actually give me a continuous function as I go from the left and the right? Do they actually match? Okay. So let's check these. And the way that we're going to check these, you can use the exact values, but I think it might be a bit easier. If we just approximate numerically. And we'll say that's going to be fine. We're just checking values here. So for this first one, I have 8 plus the square root of 48 all divided by 2. So that's approximately 7.464. Wait. Yeah. And then for my b value, we had 20 plus 3 times the square root of 48 divided by 4. That's 10.196 approximately. Okay, so let's just check these two these two limits that we were looking at. Okay, so the square root of ax squared and ax plus b, right? At -1, or really we're just checking this equation. Is the square root of a equal to -a plus b? So the two things we want to check are, is the square root of a equal to -a plus b? And then the second one was, is 3a plus b equal to 3b plus 2? Okay. So I'm going to just check that on my calculator. I'm going to say, okay, here's the square root of a. Okay. Now I'm going to look at the opposite of a. Plus b. Okay, and I say, all right, that matches up. That first one's check. Now I look at the second one. We take 3 times a plus b. Okay, you get a number. Now we take 3 times b plus 2, so we get the same number. Okay, so I say, all right, this is a perfectly viable solution set, right? So we can have, you know, this choice for A and B, right? All right, now let's look at the second one. Calculator over a little bit. Okay. If I compute A, we have 8 minus the square root of 48 divided by 2. Okay, so my A value is approximately 0.536. My value for B is 20 minus 3 times the square root of 48, all divided by 4. And I get negative 0.196. Okay, let's look at our two equations. Is the square root of A equal to negative A plus B? Okay, so I take the square root of A. Okay, and now I take negative A plus B. Okay, and there I say, oh, these don't match, right? The first one was positive and the second one was negative. So the second set of solutions is kind of a fake set, okay? And that happened when we squared both sides. Sometimes you can introduce a fake solution because squaring both sides, you know, can kill negatives. So this solution does not work. So the original problem was find the values of A and B that make this thing work, right? So for A equals 8 plus the square root of 48 all over 2, and B equals 20 plus 3 root 48 over 4, F will be continuous. Okay, as a side note, a question like this is doable in a practice exam where you don't have any sort of time constraints. On you know, exams that I write, I don't give you numbers that are going to be quite this messy, right? If I look at the work that we did, okay, so here's the problem, and I've got, you know, this first half is calculus stuff where we look at limits, and then the second half of the problem is just a bunch of algebra mess, and it's maybe more like maybe the second 2/3 of the problem is a bunch of algebra mess. Okay, exam questions aren't going to look like that. You know, you're not going to do more algebra than calculus, and you know, I'm not going to promise always, but typically exam questions are going to be nicer. Okay, let's move on to question 10. Use the intermediate value theorem to show that x cubed plus x minus 3 has a root in the interval 0 to 2. Okay, the first thing I'm going to do is write down what is the intermediate value theorem. So the intermediate value theorem says that for f, a continuous function, on an interval a, b, okay, if, and I think in our book they use the number z, So if z is between f of a and f of b, then there is a c in the interval AB with f of c equals c. Okay, and just to sort of illustrate what's going on here with a picture, if I have a continuous function, okay, let's suppose here's my a and here's my b. Right, so here's f of a and here's f of b. And you pick any y value in between f of a and f of b. So suppose I pick a z here. Then there's going to be a point on the function, right, that has that y value. And the x value for that point, c, is going to be in between a and b. Or another way to think about it is to go from a y value of f of a to a y value of f of b, we have to hit all of the y values in between. Because if we didn't, then we would have to jump over that y value. And if we jump over a value, that's not a continuous function, right? That's a jump. So that's the idea behind the intermediate value theorem. So let's look at how we can use that here. So what I'm going to do is I'm going to say I need a function. So this expression that I have, I'm going to define to be my function f of x, right? So let f of x equal x cubed plus x minus 3. The first thing in my intermediate value theorem is that f has to be a continuous function. So I need to somehow make note of why this function is continuous, and it's just a polynomial, and I know that all polynomials are continuous. Okay, so since f is a polynomial, f is continuous. Okay, in fact, it's continuous everywhere. Okay, so in particular, it's continuous on AB. And in this case, my AB is the interval 0 to 2. Okay. All right, now let's look at what is f of a and f of b, right? So f of 0 is -3. F of 2 is 2 cubed plus 2 minus 3, which is 7. Okay, so I have a negative value and a positive value. To show that this expression has a root is a 0, right? So what I want to do is show that it has a 0. So my z value that I'm looking for is 0. And 0 is in between -3 and 7. Okay, so let's look at my intermediate value theorem. For f a continuous function, got that, check. If z is between f of a and f of b, well, I've picked a number that's in between f of a and f of b, then I get my conclusion. So let's write down the conclusion. So by the intermediate value theorem, there is a c in the interval 0 to 2 with f of c equals 0. And that's exactly what I wanted to do. I wanted to show that this thing has a root or a number that when I plug in gives me a 0. And the intermediate value theorem just told me that that exists. Okay. Now, what the intermediate value theorem does not do for me, it does not tell me what that number is. Okay, so we don't know the value for c. What we do know is that it exists and it's in between 0 and 2. And later on in the course, we'll look at how you can use this intermediate value theorem to create a method for finding a 0 numerically. The idea would be I would take my interval 0 to 2 and cut it in half. I would say, okay, f of 1, does that give me a positive or a negative, right? So is my 0 in between f of 0 and f of 1, or is it in between f of 1 and f of 2? Okay, and then once I figure that out, then I cut that new interval in half. Okay, and then I keep cutting in half, and eventually I'll get an interval that is small enough that it's within the number of decimal places I want. Okay, but we'll look at that later. in the course. All right, that was number 9, or no, sorry, that was number 10. So now let's look at problem 11 here. Okay, use the epsilon delta definition of a limit to show that the limit as x approaches 3 of 6x minus 3 is equal to 15. Okay. It says specifically use the epsilon delta definition, so I'm not just doing direct substitution and saying 18 minus 3 is 15, done. What we want to do is, let's write down, just like we did before with the intermediate value theorem, let's write down what that epsilon delta definition of a limit is. Okay, so the limit as x approaches a of f of x equals L means for every number epsilon greater than 0, there exists a number delta greater than 0 such that if 0 is less than x minus a is less than delta, or another way to look at that, if you look at the x values that are within a distance of delta from a, but not equal to a, then absolute value of f of x minus L will be less than epsilon. Or another way to say that is that the f of x values are within a distance of epsilon from L. Okay, and that distance business is part of the notes that we did for section 2.5 right at the beginning, where we look at how absolute value is just talking about distance. So this is our definition. So in order to figure out what's going on here, we got to pick this apart. This says if you pick a number epsilon, then there exists a number delta. So one of the things that we need to do here is find out what delta is. Okay, so the first thing I'm going to do in this problem is going to be to find delta. Okay, the way that I'm going to do that is working backwards. So logically, this doesn't make sense from the definition I have, but this is going to be the easiest way to go to actually figure out what that number delta should be. So I'm going to start with the end here. I'm going to start with f of x minus L less than epsilon and work towards x minus a less than delta. Okay, our a value is 3, so I want to end up with something like x minus 3 less than something, and that something I'll call delta. All right, so f of x is 6x minus 3. L is 15. Okay, so I have the absolute value of 6x minus 3 minus 15 less than epsilon. Let's just do some simplifying. Negative 3 minus 15 is negative 18. Since I know my goal here is to end up with an x minus 3, I don't want a 6x, so let's factor a 6 out. And I can now see my x minus 3 in absolute values. Let's get that by itself by dividing by 6. So we have the absolute value of x minus 3 is less than epsilon over 6. So that's going to be our choice for delta. Okay, now what I want to do is I want to go through the problem again, but this time I want to go through it with proper logic. Right, so in a way that makes sense. So if you pick any number epsilon greater than 0, we let delta equal epsilon over 6. Okay, so if I'm looking at my definition for every number epsilon, then there exists a delta, and I've told you what the delta is. So I know it exists because there it is. You pick an epsilon, our delta is that number divided by 6. Okay. Then it says, if you have this thing, okay, 0 less than x minus a less than delta. Okay. So let's suppose that. Suppose you have 0 less than x minus a less than delta. Then we want to show that we have f of x minus L less than epsilon. Okay. So if I have this, the left-hand part of this tells me that x is not equal to a, but I don't really need to make use of that here. We never really needed that x didn't, wasn't allowed to be 3. I don't really need that because it's perfectly well defined here. Okay, so what I'm going to do is I'm going to look at the other side where we say, okay, this x minus a, which is 3, is less than delta, which is epsilon over 6. Now, when we were finding delta, I did a lot of steps that are all logically equivalent. F of x minus L less than epsilon is the same as 6x minus 3 minus 15 less than epsilon, just because all I've done is substitutions. And then this second one is equivalent to the third one's equivalent to the fourth one, the fourth one's equivalent to the fifth one. So I don't really have to. I could just write all of these same steps backwards. Okay? But since I've already done them, I can say, all right, well, that implies that f of x minus L is less than epsilon. And that's what I need to show that this is what the limit is. Okay, a little box to indicate we're done. All right, so it's important that we find that number delta, and then it's also important that we write this back out following the definition for what a limit is. Okay, we'll go through number 12. It's kind of the same idea. Show that the limit as x approaches 7 of 9 minus x is equal to 2. Okay, so once again, I want to start by finding delta. So I'm going to start with f of x minus L is less than epsilon and work towards x minus a less than delta. So my a value is 7, so I want to have something that looks like absolute value of x minus 7 less than some number. Okay, so f of x minus L less than epsilon is equivalent to saying 9 minus x minus 2 is less than epsilon. Doing some arithmetic, 9 minus 2 is 7. Okay, and here all I have to do is factor out a negative. If I take a negative 1 out, right, then I'll have a negative 7, and if I take a negative out of a negative x, I'll have a positive x. Because this is absolute value, the absolute value of negative 1 is just 1. So this is just x minus 7. Okay. So we're going to pick delta just equal to epsilon. Okay. So now let's look at it showing the logic. And what I mean there is here I started with the ending part, right? We want to say, if you have this thing, then I will have this. So when I start with f of x minus L less than epsilon, I'm kind of going backwards. I'm starting with what I want to show that I have. And so that's why we want to sort of rewrite it out. So for any epsilon greater than 0, let delta equal that epsilon. Then if 0 is less than x minus a less than delta, that means that x minus 7 will be less than epsilon, which, following our work backwards, means that f of x minus L will be less than epsilon. So the limit as x approaches 7 of 9 minus x is equal to 2. Okay, and as I talked about before, I understand that this is very confusing. I think conceptually this is the most confusing thing that you can do in calculus. It's not very hard computationally, but it is very hard to see what's going on and to understand what all the different parts are. So it's very helpful for building your conceptual understanding, but it takes a little practice. Okay, and then we have 3 more limits. So problem 13, find the limit as x approaches 4 of 3x plus 2 over x plus 3 minus 2, and all of that is over x minus 4. Okay, so we're back to finding limits, so we try direct substitution at the beginning. So I plug in 3 times 4 plus 2 over 4 plus 3, all of that is minus 2, and in the bottom we have 4 minus 4. So in the bottom I can see I have a 0, so direct substitution is not going to work. Let's see if it gives me any information though. 3 times 4 is 12, plus 2 is 14. In the bottom I have 7. 14 over 7 is 2, minus 2 is 0. Okay, so it doesn't look like an infinite limit, and the downside here is that I don't have a polynomial in the numerator, so I can't factor it. So we have to try something else. So let's go ahead and get common denominators. So I'm going to take this 2 and multiply it by x plus 3 over x plus 3. Okay, so we're still working with a limit. So the first limit is equal to this second limit, and I have 3x plus 2 over x plus 3. Now, when you're working with fractions, when you're getting common denominators, this is especially true if you're subtracting, but I always do this. I'm going to take this negative 2 and I'm going to distribute it right away. So I never like to subtract fractions. I always like to add fractions. And the reason that I do this is because I find if I'm going to make a mistake in a problem, it's usually going to be something very simple like losing a negative. So I like to create habits that help prevent that. And this is one of them. If I distribute this negative 2 right away before I do anything else with it, then it'll get distributed to both pieces. If I don't do that, then I'll probably end up with a negative 2x, but I probably won't end up with a negative 6, right? That plus 3 will just hang on if I just kind of jump straight into combining the two fractions together. So be careful of that. Okay, so now my fractions have the same denominator, so I can combine them together. So 3x minus 2x gives me x, and 2 minus 6 is minus 4. And rather than writing this over x minus 4, I can always think of any any expression as being over 1. Dividing by a fraction is the same as multiplying by its reciprocal. Okay, and that's helpful because here I can see, oh yeah, my x minus 4 factors will cancel. And we're working in a limit, so x can't equal 4, so that's okay. So I end up with 1 over x plus 3, and now we use direct substitution, so I get 1 over 4 plus 3, or 1/7. And again, I have a chain of equality from the beginning to end, so I don't have to summarize this, but you're certainly welcome to. Okay, and that, just maybe looks a little bit nicer. All right. a little bit close. Let's add another page here and start on a fresh page. Oops. So problem 14. Find the limit as x approaches -3 of the square root of 10 minus 2x minus 4 all over x plus 3. And, you know, I always want to try direct substitution as my first step. So we have the square root of 10 minus 2 times -3, right? And then minus 4, and then -3 plus 3. Okay, so I can see the denominator is 0. And the numerator, -2 times -3 is a positive 6. So 10 plus 6 is 16. Square root of 16 is 4. So yeah, I get 0 over 0. Okay, and again, just like the last problem, I don't have a polynomial, so I'm not going to get an x plus 3 factor. That just comes out. So we have to do something else. So what I'm going to try is multiplying by a conjugate. Okay, and the idea is that if I have something like square root of a minus the square root of b, and I multiply it by the square root of a plus the square root of b, okay, then when I FOIL that out, I'll just get a minus b, no square roots. Okay, so it's not the inside of the square roots that changes. So I don't change a -2x here. That would be a different square root, and when I multiply them, nothing nice happens. What I want to do is take the first square root and the second square root. Well, there's no square root here. I'll just leave it alone. And instead of writing a minus, I write a plus. If it was a plus, I could do the same thing by having a minus here, right? Because it doesn't matter. All right, in the denominator, we have the same thing as the numerator because we're multiplying by a fancy form of 1. And also in the denominator, this x plus 3 term is giving me a 0. I know I need to cancel it. I don't want to FOIL it out because that's going to make it harder to find and cancel going backwards. So the denominator I'm not going to do any work with. It's the numerator that I want to work with. Okay, so the square root of 10 minus 2x times that same square root will just give me 10 minus 2x. Okay, and then I have plus 4 of those square roots minus 4 of those square roots gives me 0. And then I have -4 times +4, that's -16. Okay, the denominator, nothing's going on. So let's keep working in the numerator. Simplify by gathering like terms. So I have a -2x, and then I have 10 minus 16, so that's minus 6. My goal is to cancel this x plus 3, so if I can find an x plus 3 factor, I want to. And in the numerator, I have a -2 on my x. So let's see if we can factor out a -2, and hopefully something nice will happen. So if I take a -2 out, I'll be left with an x plus 3. And now those x plus 3 factors will cancel. So in the numerator, I have a -2. In the denominator, I have the square root of 10 minus 2x plus 4. Now that we have canceled that problematic factor, we can try direct substitution again. Okay. So when I do direct substitution, I'm going to get the square root of 10 minus 2 times -3. Plus 4. So 2 times, be messy here. 2 times -3 is it's minus 2 times -3. So however you want to cut it, it's going to be 10 plus 6 or 16. Take the square root, it'll get 4. So we get negative 2/8 or negative 1/4. Okay. So the limit as x approaches negative 3 of the square root of 10 minus 2x minus 4 all over x plus 3 is equal to negative 1/4. Okay. Right, and then one last one. We have the limit as x approaches 2, 4 minus x over x squared minus 4. Oops, I don't need parentheses there. Okay. When I try direct substitution, I'm going to get 4 minus 2 over 2 squared minus 4, just 2 over 0. So we have an infinite limit again. Okay. Now, for an infinite limit, you don't have to factor things, but if you're tracking the positives and negatives, it's a lot easier when it's multiplied factors versus added things. So let's look at factoring the denominator. The numerator is already just one single factor. So I have 4 minus x in the numerator, and this is a difference of squares, so it'll factor into x plus 2 times x minus 2. So now let's look at the limit as x approaches 2 from the left of 4 minus x over x plus 2 times x minus 2. Okay. If I plug in something close to 2, the numerator is going to be close to 4 minus 2 or 2. That's positive. Okay. If I plug in something close to 2 and add to it, that's close to 4 or positive. If I plug in something close to 2 and subtract 2, it will be about 0. If we approach from the left, we have a number smaller than 2. So when we subtract 2, we get a negative. Okay. If I look at the limit as x approaches 2 from the right, then it's the same story for most of this. I'm plugging in something close to 2. So 4 minus something close to 2 is about 4. Or sorry, 4 minus 2 is about 2. If I plug in something close to 2 and then add 2, I'll be about 4. That's positive. Here we're plugging in something close to 2 but bigger than 2, so when we subtract 2, we still have a positive. Okay. These don't match. Okay. So the limit as x approaches 2, and whether we want to write it as 4 minus x over x plus 2 times x minus 2, or whether you want to write it as x squared minus 4, doesn't matter. The same limit, and it does not exist. Okay, that's the review sheet. If you have any questions, feel free to ask. We can go over them. Or if you're watching this in recording, send me an email, and I can give you a quick explanation over email or a longer one if we want to meet online for an office meeting.